Welcome to our calculus notes for 2.6b. Today we're talking about related rates and specifically related rate word problems. So in number 1 it says how fast is the area of a rectangle changing if its width is 1/3 its length and the length is decreasing at 5 feet per minute when it is 12 feet long. Now let's go ahead and draw our diagram here. So we have a rectangle and here's its length, and we know that the width is 1/3 its length. Okay, so if we're using our dreads, here is our diagram. Now we need our rates. So we know that the length is decreasing, so that's going to be dl over dt, and it's decreasing at 5 feet per minute, so that's -5. And what we're trying to find is how fast the area is changing. So what we're trying to find is dA over dt. Now the stipulation is we want to know this rate when L equals 12. Alright, so we're going to get some equations here. So one, we know the area of a rectangle is length times width. Now remember, our equation is going to be based on the rates that we have. Okay? We have the rate of length and the rate of area, and so our equation should also have length and area in it. Now we want to rewrite this in terms of just length and area if possible. So right here we can see that W equals 1/3 L. So we're going to rewrite this as area equals length times 1/3 L. And then we'll simplify. So area is 1/3 times the length squared. Alright, so that's our first goal, is get that equation in terms of the two rates that we have, length and area. Now we know a rate and a derivative is the same thing. So we're actually going to derive this. And this is the D step of our dreads. So we want to find the derivative of A with respect to time. And that means we're going to derive the other side, which is 1/3 L squared. And so we already have the derivative with respect to t solved by itself. And so this derivative, we're going to use the power rule. So it'll actually be 2/3 times L to the first power. But then we need to remember to multiply using the chain rule. So the derivative of L with respect to t is just dl dt. Alright, once we're here, we're going to use our knowns and substitute. So let's come up here and substitute. So we know we're looking for dA over dt, and it's going to equal 2/3 times L, and we're going to use the L equals 12 right here. And then times dL over dt, which is -5. So when you simplify this now, we're going to get -40, and we're going to add our units of feet squared per minute. And that is the rate of change of area with respect to time when the length is 12 feet. So it's actually decreasing by 40 square feet per minute. Alright, number 2, it says the base of a triangle is increasing at a rate of 2 inches per minute, and the height is decreasing at a rate of 1 inch per minute. How fast is the area changing when the base equals 6 inches and the height is 4 inches? So let's go ahead and draw our diagram. We have our triangle with a base and our height. Next, we'll deal with some rates that we know and are trying to find. So the base of the triangle will be dB dt, and that is increasing at a rate of 2, so that's +2. And then we know the height is decreasing, so dH over dt is going to be -1, because it's decreasing at 1 inch per minute. And we want to know how fast is the area changing. So we want dA over dt. That's what we're looking for, and we want to know this when our base is 6 and our height is 4. So we're going to substitute that in back at the end. So now we need an equation that's going to utilize these rates here. So we need it in terms of B, H, and A. Okay, so we got to have a B, an H, and an A. So what we're going to do is use our area formula. So area is 1/2 base times height. All right, well that looks like an equation with the variables we need. So we need to derive now. So we have the derivative of A with respect to t equals the derivative of the other side, which is 1/2 BH with respect to t. So now we're going to use our implicit differentiation, and we're going to solve for dA over dt. So we have our constant multiple, and then we're going to use the product rule. First function is b times the derivative of h with respect to t is just dh over dt, and then plus our second function, h, times the derivative of the first. So the derivative of b with respect to t is db over dt. Now in this case, we have already solved it for dA over dt, which is what we're looking for. So we can go ahead and substitute now. So our dA over dt is going to equal 1/2. Well, we want to know when the base is 6, so we'll substitute 6. dH over dt was -1. And then we want to know when the height is 4. And dB over dt is 2. So we just took the rates from here when the lengths are this and plugged it into our derived equation there. And when we solve for this, we're going to get 1/2 times -6 plus 8, which is 1/2 of 2, which is just 1. And so our rate is 1 square inch per minute. So the area of that triangle is increasing at 1 square inch per minute. In number 3, the length of a rectangle is increasing at 3 inches per second. If the area is increasing at 42 inches squared per second, how fast is the width changing when the length is 6 inches and the width is 4 inches? So we'll start off with our diagram, and we're going to have a rectangle, and we have a length and a width. That's about all we know for our drawing. For our rates, we know that the length is changing with respect to time at a rate of 3 inches per second, and the area, dA over dt, is increasing at a rate of 42 square inches per second. What we're trying to find this time is how fast is the width changing when our length is 6 and our width is 4. All right, so what that means is we're going to need an equation in terms of L, A, and W. So an equation that has length, width, and area is actually the area formula for a rectangle. So area equals length times width, and that's really all we can do there. So now we're going to go ahead and derive. And so we'll take the derivative of A with respect to t, and we're going to take the derivative then with respect to t of length times width. And you can see we're going to use the product rule there. So dA over dt will equal 1d2, so L times dW over dt, plus 2d1, so W times dL over dt. Now notice in this case, we're looking for dW over dt. So we can go ahead and substitute everything in and then solve for this at the end. So let's go ahead and substitute. So dA over dt is 42, and the length will be 6. We don't know dW over dt, that's what we're looking for. And our width is going to be 4, and dL over dt is 3. Now let's go ahead and solve. So we'll have 42 minus 12 over 6. And so dW over dt is going to be 5 inches per second. So the width is going to be increasing at 5 inches per second when the length is 6 and the width is 4. All right, in number 4, a cubic block of ice is melting so that it is losing 3 cubic inches per minute. So how fast is each edge changing when the block is 40 inches on each edge? So now we have a cubic block. So a cubic block has a square face, and all of the lateral faces are also going to be square. So there's really only one side length that we have here. So there's our diagram. For our rate, we know that it's melting and it's losing 3 cubic inches per minute, and that's a volume. So the change of volume with respect to time is going to be -3 because it's losing. So it's saying how fast is each edge changing? Well, that's going to be ds over dt. So that's what we're trying to find, and we want to know this when the side equals 40. So first, let's come up with our equation, and the equation needs to be in terms of V and S. So we can actually use our volume formula, and that's going to be side cubed. So now let's go ahead and derive. So we're going to get dV over dt equals the derivative with respect to t of s cubed. And deriving this implicitly, dV over dt will equal 3s squared. Using our chain rule, we get ds over dt. Now let's go ahead and substitute. So we know dV over dt is -3. And we want to know this when the side is 40. So 40 squared, and then times ds over dt. And that's what we're looking for. So we just need to solve for ds over dt. So we're actually going to have -3 over 3 times, well, 40 squared is 1600. Our 3's will cancel to 1's. So we actually have -1 over 1600 inches per minute. And that's going to be how the side is changing with respect to time. All right, number 5. Water is flowing into a cylindrical tank at 10 cubic feet per minute. If the radius of the tank is 2 feet, how fast is the level of the water changing when it is 3 feet high? Well, so here we have a cylindrical tank, and in a cylinder we know we have a radius and we have a height, and that's about all we have here. So for our rates, we know that the water is flowing into the tank at 10 cubic feet per minute, and so that's actually going to be a volume. So dV over dt is going to be 10 cubic feet per minute. We want to know how fast is the level of the water changing. So in that case, that's going to be dH over dt. And we want to know this when it's 3 feet high, so when h equals 3. Now you also notice that the radius of the tank is 2, and this is pretty important that the radius here is constant. So this is not changing, but the height here is variable because the height is changing. Okay? And we know radius is constant because in a cylinder, the radius is always the same. But the height, right, as the water level increases, the height of the water actually changes. So let's go ahead and get our equation now. So we need an equation with V and H. Well, one equation we do have is the volume of a cylinder, which is pi r squared h. Now it's okay that it has that extra r in there because we know r is constant. So r is always going to be 2, so we can just replace that constant there. And simplifying this, before we derive, we would get v equals 4 pi h. Now we can go ahead and derive. So we're going to take our derivative of v with respect to t. It's going to be our derivative with respect to t of 4 pi h. Now you'll notice here that 4 pi is just our constant. So dv over dt will just be 4 pi times dh dt. So we still have our chain rule there. So now we'll go ahead and substitute everything we know. dv over dt is 10. 4 pi's are constant, and what we're looking for is dH over dt. And notice here that the height doesn't actually even change our rates. So pretty much what that's telling me is as this is increasing, because that radius stays the same, that it's increasing at the same rate at whichever height we're at. And you can see that because there's no h in this equation. So now solving for dH over dt, we're just going to get 10 over 4 pi, which is 5 over 2 pi. And this is going to be feet per minute. So that is how fast the height is changing with respect to time. All right, in number 6, 2 boats leave from the same port at 1 p.m. The larger one travels west at 12 miles per hour, and the smaller one travels south at 3.5 miles per hour. So how fast is the distance between the boats changing at 3 p.m.? So for our drawing here, we're leaving the same port. One travels west, and the other travels south. And we want to know how fast is the distance between the boats changing. So we're going to have the distance between the boats right there. So we really get a right triangle here. And I'm just going to call this A, and this B, and this is going to be C. And that's our general diagram. So let's deal with our rates. So we know that the one traveling west is 12 miles per hour. So what that means is dA over dt is going to equal 12. And the one traveling south is 3.5 miles per hour. So dB over dt has to equal 3.5. And we want to know how fast is the distance between them changing, and that's going to be dC over dt. And we want to know this at 3 p.m. So what we could do is find a couple things here. So A at 3 p.m. will be, let's see, so time from 1 to 3 is 2 hours. And if you're going 12 miles an hour, it's going to be 2 times 12, or 24. So when A is 24. And then B here is 3.5 miles per hour for 2 hours. So 2 times 3.5, and that's going to be 7. All right, next let's go ahead and come up with an equation. And the equation is going to need to have A, B, and C in it. So for a right triangle, what we can do is use the Pythagorean theorem. A squared plus B squared equals C squared. And now let's go ahead and derive this. So we're going to have the derivative with respect to t of a squared plus the derivative with respect to t of b squared, and that's going to equal the derivative with respect to t of c squared. So using our implicit differentiation and the chain rule, we get 2a times d over dt plus 2b times dB over dt equals 2c times dC over dt. Now we can go ahead and substitute. So we've already determined that after 2 hours, A was going to be 24. So we'll have 2 times 24. And that's traveling 12 miles an hour, so dA over dt is 12. And then we also determined that B was 7 miles, and dB dt is going to be 3.5. And that's going to equal 2 times C. Well, we can also find C at 2 hours because we know that a squared plus b squared equals c squared. So C is going to be the square root of 24 squared plus 7 squared. So in this case, it is going to be 25. So you could have remembered the Pythagorean triple or just used the Pythagorean theorem. At any rate, at 3 o'clock, C equals 25 miles, and this is going to be times dC over dt, and that is what we're looking for. And when we go ahead and solve for dC over dt, we're going to get 12.5 miles per hour. All right, in number 7, water is flowing into a tank in the form of an inverted cone at a rate of 5 cubic feet per minute. if the radius is half the height of the cone, how fast is the level of the water changing when it is 8 feet deep? So here we have an inverted cone, and the water's rising because it's being filled. And so what we have is a radius, and then we also have a height. And there's our basic diagram. Now for our rates, we know that it's being filled at a rate of 5 cubic feet per minute. So dV over dt is going to be 5. Now we're trying to find dH over dt, and we want to find this rate when the water is 8 feet deep, so when h equals 8. Now we also know that the radius is half the height of the cone. So in this case, if the height is 8, the radius is going to be half of that, which will be 4. So let's go ahead and find our equation. And we want our equation in terms of V and H. So we do have the volume of a cone is 1/3 pi r squared h. Now we know that the radius is 1/2 h, so we're going to substitute that in there because we only have rates for V and we're trying to find the rate for h. So we actually get V equals 1/3 pi times the radius, which is 1/2 h squared times h. Now it's best to simplify this if we can. So V equals 1/3 pi times 1/4 h squared h. And we can simplify this one more time, and we're going to get 1/12 pi times h cubed. All right, so now we can go ahead and derive this. So we get dV over dt equals the derivative with respect to t of 1/12 pi h cubed. So dV over dt, we have constant multiple 1/12 power rule, so we actually have 3/12 pi h squared times the derivative of h with respect to t, so dh dt. And of course the 3/12 can simplify, so we'll get dV over dt equals 1/4 pi h squared dh dt. Next, let's go ahead and substitute. So we know dV dt is 5, and we have 1/4 pi, and we know we want to find this when h equals 8, and what we're looking for is dH dt. All right, so we have 64 over 4, which is 16, and we want to divide, so we actually get 5 over 16 pi equals dH dt. And if we wanted approximation, it would be about 0.0095 feet per minute. In number 8, a 20-foot ladder leans against a building. The bottom of the ladder slides away horizontally at a rate of 2 feet per second. So how fast is the ladder sliding down when the top of the ladder is 12 feet above the ground? So here's our building, and here's the ground, and then here is our ladder. Okay. So we know the ladder is 20 feet long, so we'll just put 20 there. And we know that this is going to be a right angle, and we'll just call this length x and this length y. So here's our drawing there. Now we always want to label this with variables, and we also notice that x is going to be sliding away from the wall, and if that happens, we're going to get our y also decreasing. It's going to slide down the wall. So next, our rates. See, the bottom of the ladder slides away horizontally at a rate of 2 feet per second. So that's going to be dx over dt. That's going to be 2. And we want to be able to find dy dt, or how fast is it sliding down the wall. And we want to do this when it's 12 feet above the ground. So in this case, when y equals 12. Next, let's go ahead and find our equation. And we want to be able to come up with an equation with x's and y's in it. And so we can actually use Pythagorean theorem here. So x squared plus y squared equals 20 squared. And you'll notice that 20 is constant because the height of the ladder is not changing. So when you write your equation, just go ahead and plug your constants in, things that never change. If it is changing, like the x and the y, then you leave that as a variable. Okay, so we can simplify this a little bit. We get x squared plus y squared equals 400. And now we can go ahead and derive. So we're going to have the derivative with respect to t of x squared plus the derivative with respect to t of y squared equals the derivative with respect to t of 400. So we're going to get 2x dx dt plus 2y dy dt. That's going to equal 0. Now let's go ahead and substitute. Well, when y equals 12, we can actually find x because we know our Pythagorean theorem. So x will actually equal the square root of 20 squared minus 12 squared. Okay, so if you set up a squared plus b squared equals c squared, use the values that we know, we actually get x equals 16. So we're going to get 2 times 16 times its rate of 2 plus 2 times y, which is 12, times its rate, which we don't know. And that is going to equal 0. So now let's go ahead and simplify. So we get 64 plus 24 dy over dt equals 0. And we're going to subtract the 64. And so we get 24 dy over dt equals negative 64. And then we're going to divide by 24. So dy over dt is going to equal negative 64 over 24, which reduces to negative 8 thirds. And that's going to be feet per second. Now, very important that you realize that we should have gotten a negative answer here. And the reason it's negative is that this height is actually decreasing. So always check to make sure that the rate that you get in the end makes sense for the situation here. So again, the rate of y is negative 8 thirds feet per second because it's going down as x slides away. All right, so that is our Calculus Notes 2.6b.